So just as a little bit of review here, we all need to know the conditions and conclusion for the mean value theorem. So without me necessarily quizzing you, see if you can write it down without looking in your notes. Go. Yes. What are those conditions that f has to meet?
It's continuous on the interval a to b.
Okay.
Differentiable.
Yeah. And what about the this guy's closed? That's right. Notice that if I get differentiable on the closed, then I've already got continuous on the closed as well. So if you can simply show differentiable on the closed, then you're done for everything. But this is the least restrictive. We allow f to possibly have a sharp corner or a vertical tangent or whatever at the interface. But it has to be smooth in between. That's what we're requiring. If these two conditions are met, then there's two ways to remember this. One is to simply remember the equation. The other is to remember the concept. I like to remember the concept. And the concept is that the instantaneous rate of change, which we're going to spell as f prime of c, is equal to the average rate of change, which we spell as change in f over change in x. And what we are guaranteed is that there is a c somewhere inside such that f prime of c is equal to f of b minus f of a over b minus a. If the conditions are not met, what are we guaranteed? Nothing. That's exactly right. If the conditions are met, there just is no guarantee. There might be a C. There might not be a C. We don't know. That's the way theorems work. Okay. Now, with all of that in mind, does anybody have questions on last night? Yes?
I didn't understand what you were supposed to do for 9 and 10.
9 and 10. Okay.
Let's go. Also, you could like explain the differentiable part again, like.
Yes. Differentiable simply means that the derivative exists.
So would it just be finding the derivative?
In a lot of cases, it simply is a matter of here is f prime of x, and this obviously has a value for all x's. So that's it. So let me give you examples, two contrasting examples of functions that satisfy this. Let's consider f of x equals the square root of x on the interval 0 to 1. Okay? And so if I want to, first of all, if I want to confirm that it is continuous, then I see that this is f of x is equal to x to a power. And I remember that continuity means that the limit as x goes to c of f of x equals f of c, and the limit as x goes to c of the square root of x is simply the square root of c, and so we have continuity for every single value of c in this interval 0 to 1. That's our continuity check. Now for differentiability, I actually compute the derivative, and I get that f prime of x is equal to 1 over 2 square roots of x. And I observe that when x equals 0, then this does not exist. But for any x greater than 0, it does. So I go back to my domain that I'm talking about, which is 0 to 1, and I say, hey, look at that. Although the derivative does not exist at 0, it does exist for all x's in the open interval 0 to 1. So this exists, has a value on the open interval 0 to 1, which is all that I require. The mean value theorem allows the function to maybe have, here we have a vertical tangent at x equals 0, allows for a vertical tangent at the unit place. Does that make sense? Yes. So if I can compute the derivative and say this guy exists for all the values that we're interested in, I'm good. The place where that might be tricky would be, for example, a piecewise function. You might have a joint, and so you'd have to do that joint separately. Now let me give a contrasting example. Let's say I have f of x is equal to the absolute value of x on negative 1 to 1. And so I check continuity. And I check the limit as x goes to c of the absolute value of x, which is equal to the absolute value of c, which is equal to f of c. So we're continuous. No surprise there. And then I check differentiability. And f prime of x is equal to x over the absolute value of x, which does not exist when x is equal to 0. And because this does not exist when x is equal to 0, and because 0 is smack dab in the middle of my interval, therefore this is not differentiable on the open interval negative 1 to 1, because there is one place where my derivative blows up. And we can see that in the graph. Here's the graph of f of x equals the absolute value of x on negative 1 to 1. And I have a sharp corner sitting there right in the middle of that interval. And so because of that, I am not guaranteed that there will be a tangent line whose slope is equal to f of 1 minus f of negative 1 over 1 minus negative 1. In fact, there is not one in this case. Does that help?
Yes.
Good. Okay. Well, okay, 9 and 10. So question number 9. Okay. So, sometimes this happens where you read a question and you're not really sure what it's talking about. And so what I do in that case is I try to isolate what is it that I'm confused about in the directions. So can you identify what you're confused about in the directions? And if you're saying to yourself, well, the whole thing, then that means that you need to spend a little time focusing more on what it is that is confusing to you. Here we have function f of x equals x plus 1 over x. And we have an interval, which is x is between 1/2 and 2. And now what do they want us to do? Okay.
I think it was just almost like variables,
Are you talking about in that sentence?
yeah,
Okay.
like in the directions.
Oh, you're supposed to find the equation of the secant line? Is that how
It
these?
says, so for in exercises 9 and 10, the interval A is less than or equal to x, which is less than or equal to b is given. Let A equal A comma f of A and b equal b comma f of b. And then write an equation for A, the secant line AB, and B, the tangent line to F, and the interval A comma B that is parallel to AB.
Okay. Good. So when I'm reading math and it's not making sense, it's usually because I don't know what a symbol refers to. And it looks like that AB is tripping you up. So can we go back to the stem of the question and find anything that tells us what A and B are supposed to be? Do you see something that tells you what A is supposed to be? Yes, exactly. Specifically, A is supposed to be the point A comma f of A, right? And B is supposed to be the point B comma f of B. Well, now that raises a new question. What are these little a and little b right here? Yes, that's exactly right. The a is this guy and the b is this guy. Exactly. Remember that math is driven by substitution. If a is 1/2, then gosh darn it, a is 1/2. And so the way that I make sense of these questions is I now come back and plug in to get as much clear definition on this as I possibly can. Can you compute f of 1/2? Of course you can. What do you get? Two and 1/2, 2.5. And we do the same logic here. We get 2, and what is f of 2? Also 2.5, which is kind of interesting. Almost like they planned it that way or something. Okay. And now what we have done is we have taken our question that was much more confusing and we have brought clarity to it. I see Evan's head going, now, yes, I get this problem now. And all that she did, all that I had her do, was to simply substitute. That's it. Substitution brings clarity. If you can find something that says A equals, then let A be that thing. So now we have a much easier question. Find the equation for the line that connects these 2 points. I'm pretty sure you can do that in your head, in fact. What is the equation for that line going to be? Slope is 0, which greatly simplifies matters. That's okay. There's supposed to be an aha moment that's going on here, so everybody should be finding the equation in this line. Yeah, there you go. That's it. Y equals 2.5. And the logic of it is, if my y value is 2.5 here and my y value is 2.5 here, there's only one line that's going to go through both of those at 2.5, and that's y equals 2.5. It has a slope of 0. There it is. Okay? So having done that, now they ask you in part B to find a tangent line that is parallel to. Notice that there is no reference to the mean value theorem here. Even though they're talking about secant lines and tangent lines, they're not asking you to verify that the conditions are met. As it turns out, we can do a quick check mentally and say, hey, look, we've got a rational function plus a polynomial. It's continuous everywhere except at 0. and its derivative will be a rational function plus a polynomial, also exists everywhere except 0. So it is differentiable and continuous. Mean value theorem is met. We can do that, but we didn't have to in order to answer this question. They want us to find the equation for a tangent line that is parallel to the line AB. So what do I need? So I need slope, that's right. And I need the slope is equal to 0 because AB has a slope of 0. And where do I find the slope of the tangent line? Bingo, that's right. So I'm going to begin with this equation right here. And this equation expresses, this is the way the cool mathematicians say that the tangent line is parallel to the secant line. Because the tangent line slope, f prime of c, is equal to the secant line slope, which in this problem is 0. Keep going with that thought. Very good. That's right. F of x is equal to 1 over x plus x. She goes through and takes a derivative term at a time to get negative 1 over x squared plus 1. And f prime of c is going to be negative 1 over c squared plus 1. Okay, solve the equation. Don't stop with your algebra. Do a domain check on the answers. Tell me how.
Well, I did 1 over c squared equals 0. Or, yeah. No, equals 1.
Ah, okay.
And then I made it.
Okay. Don't you also get c equals negative 1? Ah, okay. So we need a way of doing this that doesn't leave us stranded like that. I like clearing the fractions. Multiply both sides by c squared. And when you multiply both sides by c squared, you get a much friendlier equation. C squared minus 1 is equal to 0. And this factors now into c plus 1 and c minus 1. So that c is equal to 1 or negative 1. However, now that we have our answers, we need a domain check. Are both of these answers actually valid for the domain of our problem? Negative 1 is outside our domain. So we end up with c equals 1 as our one location. What does this mean, that c equals 1? What this means is that there is exactly one point on the curve where the tangent line is going to be parallel to the secant line, and that's at c equals 1. Great, I found c, but that's not the equation for my tangent line. What else is needed? Okay, so I've got a slope, which is 0, and I have a point. And what is my point?
0,
We lost track of the plot here. Actually, it's the c value that we're looking at. That's the point where our function is. So it's actually 1 comma f of 1. And what is the value of f of 1? 2. And so now we're ready. Y minus y1 equals slope times x minus x1, and we get y equals 2 as the horizontal line that goes through. Once we're all done, sketching this thing gives us a much better sense of our handiwork. When we sketch, here comes our curve from 1/2 to 2. And what we have is the horizontal line y equals 2.5, like so. And down here at x equals 1, which I think is actually the minimum on the curve, drawing not to scale, we have a horizontal tangent. In fact, it is the minimum on the curve because it's a horizontal tangent. The place where y prime equals 0. Changes signs from minus to plus. Okay? So the moral of our story is that substitution is a fantastic way to get better understanding. And the process that we are engaged in is learning how to better read math. I mean, that's a process that goes on. And so today was a step in that direction. How are we doing? Are there any other homework questions? Just like none. Where did we go? There's nothing wrong with it. It's just gonna go. Number 13 is a good example of what I call the physics use of the mean value theorem. And here's what I mean by this. If you are measuring something physically, it is impossible for you to measure an instantaneous rate of change, because you would have to do the limit as delta t goes to 0, and there's no physical way to let delta t approach 0. That's a mathematical concept close to 1. So what physicists do is they measure, if they want to measure speed or velocity, for example, they measure velocity as an average velocity, which is delta x over delta t, and they try to make their time intervals as small as possible. Okay? Now, because this is an average rate of change, some smart aleck might come along and say, but that's not really your velocity. That's not really your instantaneous rate of change. And the physicist's comeback is to say, look, my position is a continuous and differentiable function. Therefore, sometime in my time interval, t0 to t1, my velocity has to equal the average velocity. So the way the physicist uses it is he computes the average rate of change, and he says that is a good estimate for the instantaneous rate of change, because it is true that somewhere in that time interval, my instantaneous rate of change equaled my average. That's the spirit of the mean value theorem. So now let's take a look at our trucker. Our trucker traveled how many miles in 2 hours? Uh-huh. Oh, is that it?
Yeah, it's a ship.
Put that with the wrong problem.
Cruise ship. 184 sea miles and 23 acres.
Ah, okay, yeah, I was looking at 11.
Explain why it takes 7
So we have 184 miles in 24 hours. So a physicist looks at that and says, I can compute what from that information? I can compute average velocity. Exactly. I can compute that the average velocity was 184 miles over 24 hours. And when you actually do, what number do you come up with? 7.6 miles per hour, which is knots. Exactly. And so looking at this, since my average velocity is 7.6, it must have been the case that my instantaneous velocity was 7.6 at some time during that time period. Okay? That's the mean value theorem talking. Now I look at the problem, and the problem asks me to show that there must have been some time during which the velocity exceeded 7.5 knots, and this is certainly exceeding 7.5 knots, and we're done.
Because I did all the things, but I don't know how to like answer the question.
How to construct the
Right,
answer.
yeah.
Yeah, Yep. So I would do it like this. I would say V average is this. And then I would say, since position is continuous and differentiable, and you can take that as a given. Here's what this means to say that my position is continuous and differentiable. It means, first of all, that you can't teleport. And second of all, it means that at any time you have a speed. You have a velocity. Since position is continuous and differentiable, the mean value theorem guarantees a time for which V equals 7.6. And if you want to be, okay, so this is the perfectly fine answer. If you want to be really, really picky about answering exactly the question that they said, which is greater than 7.5.
Okay.
And that shows that we are exceeding 7.5.
Okay. Thank you.
Yep. Good. Any other questions? How do you find these problems? Generally speaking. Not too bad. What's that? Yeah, they are. Exactly. Okay. I want to show you a mathematical use for the mean value theorem. And that is to prove results that are useful in other areas. The mean value theorem is kind of like a core driving idea that gives us a whole bunch of other things that are very, very useful. And one in particular that we've already been using is the notion of increasing and decreasing. The mathematical use of the MVT is to prove other theorems. And in particular, one theorem that we have is this. We have said that if f prime is positive on an open interval a to b, then f of x is increasing. On the interval a to b. Now, as I have said this, all of you have nodded your heads, yes, because you can intuitively see that if I draw a curve so that the tangent line slopes are always positive, then that curve has to be going up, right? That's just sort of an intuitively satisfying result. And in terms of mathematical history, up through the 19th century, honestly, from when Newton and Leibniz invented the calculus all the way up through the 19th century, mathematicians were content to say, yes, this makes sense. What happened in the 19th century is people started pushing boundaries. They do this in every field, right? So you have something like, I don't know, skiing as a sport. And pretty soon you have extreme skiing as a sport, right? People push boundaries. And the way that people pushed boundaries in the 19th century is they started coming up with really crazy functions. So, for example, Weierstrass managed to come up with a function that is continuous at every point and is not differentiable at any point, which is really crazy to think about. You can't even visualize that. But basically, it's kind of like infinitely wiggly at every point. And so the question is, with these really weird functions around, maybe it's not always true that a positive derivative means that the function is increasing. And so that led, Weierstrass in fact led the charge in terms of making sure that all of our results are mathematically proven. That had to get modified a little bit in the 20th century when we began to understand that ultimately systems have to have some unproven axioms that they rest on. There have to be some just basic results that we all go, yes, I can't imagine it any other way. Things like 1 plus 1 really does equal 2. Those sorts of things. However, this is a result that can be proven, and it's proven by means of the mean value theorem. And the way I'm going to prove it is like this. I'm going to prove that it's impossible for our theorem to be false. I'm going to prove that it's impossible for a function to be to have a positive derivative and not be increasing. Does that make sense? So we're going to start by supposing that f is increasing, but it does not have, that f is a positive derivative, but it is not increasing on a to b. And I'm going to show that that is ludicrous. It is impossible. Okay, so suppose that f prime is greater than 0, but f of x is not increasing, specifically on a to b. Now what does it mean that f is not increasing? It means that for some value somewhere in here, here's my a and here's my b, and I have some value here where f of x actually goes down instead of up. Okay? Let's call those values c and d and state that fact. So f is not increasing, then there are a c and d such that f of d is less than f of c, but, or maybe less than or equal to, right? Could be it's on the same level, but d is bigger than c. So what it means to be not increasing is that as you go to the right, instead of going up, you either stay on the same level or you go down. And this is how we would say that mathematically. Does that make sense to everybody so far? Okay. And now I'm going to apply the mean value theorem to f. First of all, can I apply the mean value theorem to f? Well, it has to be continuous on the closed and differentiable on the open, right? But the way the question was stated to begin with, I know that f prime is greater than 0 on the entire interval a to b, which includes the interval c to d. And so f is differentiable on the closed interval c to d, and therefore it is also continuous. So the question itself presupposes that the mean value theorem applies. So let me state that. Since f prime is greater than 0 on a to b, f is continuous and differentiable on c to d, which is a subset of the interval a to b. Okay? So the mean value theorem applies, and now I'm going to apply it. That means that there is a point and I've already used the symbol C, so I don't want to reuse that. Let's use a different symbol, maybe K. k works. There is a point k, x equals k, such that f prime of k is equal to f of d minus f of c all over d minus c. The mean value theorem guarantees this fact. But now what can I say about the sign of this quantity here on the left, on the right? D is bigger than C, so D minus C has what sign? Positive. And f of D is less than f of C, so f of D minus f of C is negative, or if they're equal, then it is equal to 0, right? So if I take a negative number and I divide it by a positive number, what am I going to get? A negative. And if I take 0 and divide it by a positive number, what am I going to get? 0. So no matter what, this quantity right here has to be less than or equal to 0. But wait! Stop! This is impossible! Because we already know that f prime of x is what? Is greater than 0 on the entire interval a to b. And yet, if f is not increasing, the mean value theorem guarantees that there will be a point k where f prime is either negative or 0. That's not possible. Because it is not possible for f prime to be positive and for f not to be increasing. You see the logic there? What is he thinking? Okay, very good. In math, we say this is a contradiction. And once we hit a contradiction, we know, therefore, it is impossible for our supposition to be true. I can't suppose that f prime is positive and f is not increasing. It makes no sense. It's like supposing a square circle. So therefore, if f prime is greater than 0, then f must be increasing. Because it can't be not increasing. And that's the end. And the use of the mean value theorem pretty much always looks like this. We use it to prove some theorem by computing an average rate of change and saying, you know what, that has to equal the instantaneous rate of change. We're going to see this idea again later on when we do integration. And we're actually going to, I might have time, yeah, I do. I have just enough time to give us a little bit of a jump start on what we're doing on Monday. Your homework tonight is going to be kind of familiar. It's going to ask you to walk through and find places where f is increasing, decreasing, or finding out stuff. It's going to be basically practice of the stuff that you're doing. So that'll be nice. So let me give you a sneak peek of what's going to happen on Monday. On Monday, we're going to begin to consider the reverse question. Suppose I give you the derivative of f prime. Can you find the original f that it came from? I call this derivative jeopardy, or antiderivatives. So, for example, right. Suppose I tell you that the derivative of a function is x squared. What is the original function? I want you to take 30 seconds to try to answer that question. Do it with a little guess and check. And see if you can come up with a function whose derivative is x squared. Okay. How many of you have such a function? Only 2 of you? How many of you have such a function? Okay, give me your function. Good. Let's check it. Does it check? Yes, it does. Do you have a different function? Same one. Does anybody have a different one?
1/3 x cubed plus 1.
Ah, let's check it. Does that work? Yes. Does anybody have a different one? Yes.
1/3 x cubed plus 2
All right.
Whoa. No, Chelsea, you can keep it there.
Okay. Does anybody have a different one? How about 1/3 x cubed plus the sine of e to the pi?
Okay.
Does that work?
Oh.
Yes, it does. That works. Any constant will do. Do we agree that 1/3 x cubed plus any constant will satisfy this? Now we notice something very uncomfortable. There is not a unique answer to this question. There's more than one answer to this question. And so this raises a really interesting problem. Is there some other function out there whose form I can't even imagine, whose derivative is also x squared? Maybe there's some combination of sine of e to the square root of something or another, and when you take its derivative, poof, it's x squared. Could that be? The mean value theorem is actually going to answer this question for us. And it's going to do it in this way. It's going to lead us to a theorem that says,
What's the reason here?
actually it just has a statement, that's all. If two functions have the same derivative, if f prime is equal to g prime, then f equals g plus a constant. In other words, the answer to our worry is no. In fact, there is only one function within a constant that satisfies f prime equals x squared. And that function is 1/3 x cubed.
Basically, they're kind of finding out how it is.
It is, yes, it's guaranteeing the obvious. It's going from our intuition, we suspected probably not, to now we know, definitely. And that's useful for us. Do you guys remember having to take those derivative quizzes? All of you had to take them, or many of you had to take them at some point. And all of you have had to take derivatives at some point. And you took the derivative of some weird function, and it came out to be 1. Well, that should bother us, because I know the function whose derivative is 1. What is that? X. And so if my original function was not x to begin with, plus a constant, then I should not end up with 1 as my final answer. So it provides us with a way of checking ourselves. See what I'm saying? More on this on Monday, assuming we have school Monday. See you later.